Hello, and welcome to this presentation from Dr. Boris Gorbanov and Michael Burton of Ancon Technologies. The topic we will be discussing over the coming slides is counting individual ions by tagging them with nanoparticles. This presentation will show an overview of examples and limitations of currently available methods for quantification of ion concentrations in the air, a description and the working principle of the novel method termed individual ion tagging, or IIT, and its comparison with the Faraday cup, tests on the IIT undertaken in the Boulby Underground Laboratory, and possible applications and future development of the technology. At present, there are a selection of methods used in quantification of ion concentrations in the air. These include the Faraday cup detector, which is a metal device designed to catch ions in the air and is widely employed in mass spectrometers, ion counters, and many other instruments. The electron multiplier, which works within a vacuum, multiplying incident charges between metal plates and generating electric current. The Geiger counter, which is an instrument for detection and measuring ionizing radiation by utilizing the ionization effect produced in a Geiger-Müller tube filled with low-pressure argon, helium or neon. And finally, semiconductor detectors, which measure the effect of incident charge particles, or photons, to quantify ionizing radiation. Measurements of ion concentrations in the air using these and many other methods have one common feature: amplification of the electric current. Conventional techniques are close to their physical limits of detection due to thermal fluctuations in the electron gas of metal conduits. This means it is extremely challenging to measure concentrations below the parts per trillion level in the air, and therefore restricts progress in trace concentration measurements in many areas. A novel concept of measuring concentration of ionized molecules in gases has been recently discovered, providing a breakthrough in sensitivity. This concept enables detection of individual ions at atmospheric pressure by tagging with readily detectable nanoparticles, thereby enlarging their size. This concept was termed individual ion tagging, or IIT. Here, we would like to explain the concept of IIT. The first stage in the process is the physical tagging of the individual ions. The small blue circles in this diagram show the positively charged ions. The large green circles indicate neutral tagging particles. In the red circle, an ion is colliding with a tagged particle, forming a complex. This tagging process increases the volume of an ion by 1 billion times, thus making the now tagged ion more easily detectable. The second stage is the extraction of the tagged ions. The bold black lines shown to the right of the screen are electrodes in the extraction chamber that form an electric field. This electric field attracts the charged tags to the optical particle counter, whilst the remaining neutral tags are removed, as shown with the green lines. Finally, with the optical particle counter, the tagged ions are able to be counted individually by detecting the scattered light from the tag. The signal does not need amplification and allows sensitivity of up to 1,000 times greater when compared against the Faraday cup and other methods. For this concept, an individual ion counter has been designed as a detector that can be used with any ion separation means, for example, mass spectrometry. The image shown here is Ancon's nanotechnology molecular tagging, or NMT unit. Replacement of a conventional ion detector with an individual ion counter increases sensitivity of ion detection by around 1,000 times. This diagram is a schematic of the individual ion counter device. The green dashed lines show the neutral tagging object trajectories, and the tagging chamber is shown with a circle. The blue dashed line schematically shows the ion trajectories within the tagging chamber. The red dashed lines indicates the direction of the tagged ions, which were formed in the tagging chamber as they passed the electrodes. This concept was realized in a setup containing 4 modules: a tag generator, a tagging chamber, a tagged ion extraction chamber, and an optical particle counter. The first module is the tag generator, where spherical particles around 200 nanometers in size are formed by homogeneous nucleation from a non-toxic, odorless organic compound. The generator comprises of a stainless steel condenser and a glass saturator with a heater. The second module is the tagging chamber, which is a stainless steel cylinder with two inlets and an outlet. A sample flow containing ions enter the tagging chamber through one inlet, and the flow of tags enter the chamber through the other inlet. As we explained previously, the charged ions are attracted to the neutral tags, binding and enlarging their size. The third module is the charged tag extractor, formed by two stainless steel plates and a spacer. When an electric field of sufficient strength is formed between the electrodes, the now charged tags are separated from the remaining neutral tags and moved to the optical particle counter, or OPC. Finally, the tagged ions are individually counted in the optical particle counter. Because the number of charged tags is equal to the number of ions, the OPC reading provides the ion number. This enables a single ion to be counted without any electric current signal amplification. The following schematic shows a comparison of the setup of the IIT method against a Faraday cup-based electrometer. The radiation sign indicates the ionized chamber with americium-241. For this experiment, the same source of ions was used to compare performance of the Faraday cup and the IIT sensor. A gas flow was employed to transport the ions from the ion source to a detector. To achieve a controllable range of ion concentrations, the length over which the ions were transmitted was varied, and the number of ions reaching the sensor at the end of the tube altered due to ion losses. This graph shows how the ion count rate data from the IIT ion counter compared dependent on the copper tube length. The blue squares represent counts obtained with a radiation source present, and the red circles show counts for when the radiation source was absent. As you can see, the ions were shown as detectable from 0 to 100 mm in the entire pipe length range. Using the same experiment, the Faraday cup device was tested with results as shown here. Again, with blue squares showing the count occurring when the radiation source is present, and red circles for when the radiation source was absent. This experiment demonstrated that with a Faraday cup electrometer, ions could only be detected in the pipe length range up to 30 mm. The IIT method of attaching ions to tags can provide a breakthrough in sensitivity by enabling a single ion to be detected. This experiment example showed a much greater sensitivity of the IIT compared to a Faraday cup electrometer. Further measurements equivalent to 30 attoamps have been recorded with IIT. In this slide, an example of absolute ion current measurements is shown using the NMT ion counter with varying copper tube length. The green squares represent the count occurring when the radiation source is present. As demonstrated, results obtained in comparison of the two methods show that the IIT enables detection of ions down to 30 attoamps, but the Faraday cup electrometer detects only down to 2 femtoamps. When used for the purpose of detecting ionizing radiation, such as cosmic rays, the IIT concept enables the ionizing radiation to be detected. Cosmic rays form ions in the air. If the air is filled with neutral tags, then the ions formed will be tagged, as we described earlier. This schematic demonstrates the closed-loop IIT ion counter with an external flask for detection of ionizing radiation. The neutral tagging object trajectories are shown with dashed green lines. The flask is shown with a thin-walled grey circle, and the dashed red line indicates the direction of the tagged ions. Here, we have provided an example of cosmic ray detection conducted in a laboratory at the University of Kent using IIT. The bottom right shows IIT counts against time parameters for a stainless steel external flask of 80 cubic centimeters in volume filled with air. It was shown that the height of peaks is influenced by the energy and type of cosmic ray particles. The Bulby Underground Laboratory is situated in the Bulby Mine, which is 1,100 meters below the surface of the ground. It has been developed for experiments requiring extremely low ionizing radiation environments, such as dark matter, and detection of weakly interacting massive particles. The portable IIT unit was tested in the Bulby laboratory to evaluate detection limits of the tagging method. Measurements of ions formed by cosmic rays above ground were taken at the Bulby laboratory site. This graph shows the IIT ion count rate against time for the use of external flask of volume 20 cubic centimeters, demonstrated by the dashed line, and 1000 cubic centimeters shown as the solid line. As you can see, there are many solitary peaks observed with flask volume of 20 cubic centimeters associated with cosmic rays. As comparison, the same IIT measurements were taken in a cosmic ray-free environment within the Bulby underground laboratory. This simplified schematic shows the closed-loop IIT inside a lead castle. An example of the IIT count rate versus time for external flask of 1000 cubic centimeters within the lead castle in the underground laboratory is shown here. The origin of a peak is very difficult to identify, and it is unlikely that it is caused by traces of radon gas or cosmic gas due to the site controls. The IIT was further tested with cesium isotope within the underground laboratory to demonstrate detection capability of the device. Concealed in a lead container, a cesium isotope source was placed in the vicinity of the flask at 210 seconds, here marked with an arrow. The ion count rate measured indicates the possibility of measuring of an extremely low electric current equal to around 1 elementary charge per 100 seconds or 1.6 zeptoampere. This level of electric current at atmospheric pressure is extremely difficult to measure with conventional methods. In summation, the individual ion tagging breakthrough in sensitivity of ion detection opens new possibilities in many areas. For example, one such application of the IIT could be detection of high-energy cosmic ray particles with energy above 10 to the power of 16 exposure value, which is highly challenging using conventional means. There are no physical limitations to building an IIT detector, which may help in finding the maximal energy of cosmic ray particles, the Greisen-Zapspin-Kuzmin limit. There is no reason why IIT with an extra large external volume could not be applied for detection of weakly interacting massive particles in environments where cosmic rays are not present, such as deep underground mine laboratories. To illustrate this, the schematic here shows a large external volume connected to an IIT device in order to detect very low flux events. A large external volume designed with a high aspect ratio would be sensitive to the direction of high energy particles, and as such should be in a low background environment where low energy cosmic rays and other natural man-made sources of ionization are eliminated. An external volume, as shown on the right, generates a larger signal if a particle travels along the length, demonstrated by the red line, rather than along the diameter, shown with the green line. This concludes our presentation of the IIT concept of counting individual ions by tagging them with nanoparticles, and we would like to thank you for your attention. If you have any questions or comments regarding this presentation and the technology, please contact a representative from Ancon Technologies with the email address shown or by visiting ancontechnologies.com, and we will be happy to assist you. Thank you.